My name is Katie Yu, and I'm from Portland State University. And today I'm presenting a framework for analyzing rate adaptation algorithms. So rate adaptation algorithms change modulation in response to different channels conditions. There has been a lot of rate algorithms being developed in the past, but there's lack of theory how we can compare them in different channels conditions. So this research is the first step towards developing an abstract model to allow us to estimate the performance of different rate algorithms, and also to allow us to make general statements comparing a pair of algorithms' behavior in different channels conditions. So we first define two metrics to encapsulate and rate algorithms' performance. First is the speed of adaptations, which means that how fast it can adapt. And second, the quality of adaptations, which means that how well it adapts. So first, we categorize the adaptivities of rate algorithms. For example, this is the mobile channels for a person who walk back and forth. And the blue shows that the SSI values of the channels, and the gray indicate the rate changes in sample rate. As we can see, that the rate algorithm is trying to adapt while the channels is changing, and it impacts the throughput. And this is another example when we turn on the microwave and trying to interfere with the channels. And this figure shows that the rate algorithm starts dropping packets while the microwave is interfering, and while the channels become better, and the rate algorithm starts adapt in a higher rate. So in general, low rate is being used in a poor channel conditions, and high rate is used for good channel conditions. So in order to study rate adaptations, we need to identify events where the channel changes significantly to force the rate change. So we define quality of adaptations as difference between the optimal throughput and the throughput achieved using the rate provided by the rate algorithms. So the metrics that we describe here in the figures are T, time taken by the rate algorithms to adapt, and delta, the difference between the optimal throughput and the mean achieved throughput after the rate algorithm has adapted. So in order to study rate adaptation behavior, we need to first be able to create repeatable experiments. So how are we going to do that? So we create the same channels conditions with the following properties. So the channels has to be is to be long enough stable behavior such that the rate can change and be able to adapt to certain rate before we force a change. So for example, square wave is a very good example, which we will show later. And it can test how the algorithms behave. And similar channels conditions need to be used to measure T and delta we just talked about. And the period of the square wave as well as the amplitude need to vary in order to study the impact of T and delta. So this is a square wave. And as you can see, this grade is the RSSI value. The dark line is the optimal throughput. And the dark blue line is the actual throughput. So we define the square wave, the T down when from RSSI value high to low, as indicated here. And the period is just the wavelength. And this is T up. And the delta is the difference from the optimal and the actual throughput. And now we create the repeatable channels model. So we exploit the ability to change the transmit power in MAC Wi-Fi on a per packet basis to create these different channels conditions. So the sender and receiver are placed in the same location for all experiments. And we use iPerf to generate UDP traffic, and each packet is 1,450 bytes in size. And at the server, we dump the RSSI value each packet received along with the timestamp and the rate that each rate algorithm used. So now, how are we going to find T and delta? So we use a 100-second period in square wave because it allowed us significant time to reach the steady state, high to low or low to high, before we force a change. And our SSY value difference, we use 17.5 dB, 15.5 dB, 13, and 9 dB. So large job of our SSI will result in high packet losses and cause faster adaptations, while smaller changes will take longer time to adapt. So each experiment we repeat at least 5 times for 3 different algorithms and 3 different channel conditions. So we test ONO, sample rate, and AMR, which is implemented in Mac Wi-Fi. We use a relatively unused channel to minimize the effect of back-off. To quantify the performance of rate algorithms, this is the result that we do for all the delta value and T value, both adapt up and down for 3 rate algorithms and for different RSSI values. So as we can see, in general, T down is generally smaller than T up, because when the RSSI value falls significantly, the high rate being used caused by packet loss and force the rate algorithms to adapt quickly. And the delta, which is the quality, how well the rate algorithms adapt, in general is very good, and it's about 0.7. And some of them are 0.4. So now we are going to use this value to estimate the throughput. So given an RSSI pod, we create a pod of optimal throughput using 1 second bucket. And then we convert the T data and the slope values, gamma, that describe the rate of the change in megabit per second, and use a linear model to determine the throughput for the transition period and to determine when the algorithm being stable. So the above step will already tell us the time period when the algorithm being adapted, as well as the period when the algorithm has stable. So for this stable period, we estimate the throughput by multiplying the optimal throughput with the delta that we used.